In this video, I'm going to show you why the data isn't always what it seems to be. In particular, for some time now, I've been battling oil temperature issues in my Fiesta K24 turbo powered track car. So let's get into it. Let me show you some data from a track day I did recently in March at Snotrocket in the UK, and I'll show you what I mean about oil temperature issues. So if I go into my log viewer as part of my Bowders Control Systems ECU, we'll create a new chart. Let's just take some typical variables. So we'll have engine speed, which is generally what you want in most charts. So this is engine speed over a few different log files. This goes up to 16 minutes. This will become more obvious in a second. Right, so I'm going to add another chart underneath here. Let's change that to oil temperature, as that's what we really care about. And then just for fun, let's have oil pressure below that. Pressure is here, and we'll get rid of oil temperature. Okay, now this is three really useful bits of information over time. Just going back quickly to give you some backgrounds. The car used to have the original Honda OEM heat exchanger that kind of goes between the oil and the water, so that the engine coolant heats up the engine oil quicker, which is good for a wear and emissions perspective. And then once everything's up to operating temperature, oil and water around 100 degrees, they kind of help normalize the temperatures between themselves. But it's a really small heat exchanger. It's not designed for heavy sustained track use, and it's mostly for emissions and engine wear. So I looked at replacing that with some kind of passive oil cooler separate to that, and I'll go into how I've done that here. So I picked up a Setrab oil cooler here. It's 115 millimeters wide and it's 25 rows in depth. In theory, that would have a lower oil pressure drop across it rather than a big long cooler that goes all the way across the front of the car. And I decided to put a fan on here. This is a spout fan that would be ultimately controlled by the ECU to help regulate the oil. Very limited places to put this on the car. So this is here behind the front fog light assembly, and on the right here, this is the inner wheel arch liner. There are some holes in it, some vents, but I'm probably going to open that up a bit more in the future and maybe try and duct this better than what it is. On the back of the engine, so this is a sandwich plate from T7 Design. This is what feeds the oil cooler where it's mounted. And this here is a Bosch 10-bar oil pressure sensor combi with a temperature sensor in it. And this is where we're getting the data from. And when you look here, this is the view of the oil cooler through the duct that I made on the fog light on the front of the car. And going back here, you can see that here. It's behind this duct hole here on the front of the car. So that's this setup. We've got the oil cooler. It's thermostatically controlled on the sandwich plate, and it's not massively ducted at the front. It's got a hole, and that's about it. But this was the first test on track with this package. Anyway, right, so going back. So looking at the stints here, there were two separate stints. That's why we've got these two kind of humps. So this first 5 minutes here on the graph, this is basically hard on it on track, and then this is the cool down period, and then a second stint going out again, and then there's a cool down period. This is an easy way to see it. It's basically two separate, like 5 minute stints, 1, 2, 3, 4, 5, maybe 6 minutes on the second stint. And just for information, the first stint didn't have the fan active on the oil cooler. The second stint did have it on, and you can see there's a slight different change in the rate of increase in oil temperature over time between the two tests. So the fan definitely seems to do something. It definitely slows down the rate of increase in oil temperature, but you can see that it's only when I start lifting and slowing down that the oil temperature really stops climbing. So oil cooling isn't sufficient at the moment, but this is definitely some good data. And just for interest's sake, oil pressure here at the bottom, you can see that as the oil temperature goes up, the average oil pressure starts to drop as well, which is typical. As the oil thins out, the pressure drops out of the pump. And that is something that you need to keep an eye on, because if the oil gets too hot, the pressure can get too low, and then you can have engine damage. For those that may be familiar with how engines work, looking at this oil temperature graph, it's a bit weird, right? So, and just to demonstrate why that's weird, I'm going to add another value in here, right? I'm going to add coolant temperature. So, and let's put these on two discrete plots so that we see them side by side. Now, this is really interesting. I'm going to get rid of oil pressure now, because then we can see this a bit easier. Now, when you look at these two charts, oil temperature in green, coolant temperature in red. Sorry if you're colourblind. I know these are probably two of the most common conflicting colour schemes. But what is important here, the lower graph here, it looks a lot smoother, right? So it goes up and down, and it cools down as we slow down on the sprint. But the green line for oil temperature is very up and down. Now, anybody that knows basic sort of mechanics or engineering, or was paying attention at school, fluids don't change temperature that quick, right? Under normal operation in an engine. And the shape, if I zoom in a bit here, the shape of the curve for coolant temperature, the bottom line, it's quite smooth. It goes up and down, but there's no sharp spikes in it. However, when you look at oil temperature, it goes up and down very rapidly, very, very rapidly. And that's a bit weird, right? Oil doesn't change temperature that quick. And to give you an idea, if we zoom in a bit to just 10 seconds, you can see up here the engine speed's going up. Let me add another chart on here. Now let's put the throttle in so we know when we're full throttle. So this red line now at the top, the second one, this is basically the throttle position. And you can see here going full throttle, and then we're going up in one gear, changing gear, going up in another gear. And the oil temperature, if we look here from the point we go on the throttle here, just in one gear, the oil temperature, where are we, down here, it's changed from 118 degrees to 130, right, just in one quick gear, right? And that seems a bit excessive, but what's more important is the rate of change. So if I go here, there's the timer, so just in 1 second, we look here down the bottom, there's 1 second, that oil temperature has changed 8 degrees in 1 second. That just doesn't happen. Oil temperature doesn't change that quick. I mean, we can zoom in even closer. Look here. We go right in here on the data. This has changed in 0.6 of a second. The oil temperature has gone from 123 to 128. It's gone 5 degrees in 0.6 of a second. Never happens. Oil changes temperature slower than coolant, and as you can see, the coolant doesn't change, right? That's changed 0.2 of a degree in the same period. And water changes temperature quicker than oil because of the viscosity difference between them. So just to summarize, so we've got coolant temperature, looks pretty normal, it goes up and down, it's pretty smooth. Oil temperature doesn't look right. It looks like a noisy signal. If you're used to looking at digital signals, or looking on oscilloscopes or whatever, you'll probably see lines that look like this. So I thought to myself, what could be causing that? And in this video, we're going to ultimately retrace the steps that I took to understand the root cause of my oil temperature issues, which may not have appeared what I first thought. So I was trying to see, well, what's influencing? What are the common patterns here with these spikes in the oil temperature, right? So I go, you can see up here on the second stint, the changes are quite significant. So I thought, what's the common issues? So if I take, this spike here, this is an obvious spike here, between this point and that point. And then when you look up at the engine speed, you can see that's going through probably 4th, 5th and 6th gear, up to about 125 miles an hour, I guess, by the end of where we are here. And the throttle was flat out, so I'm using flat foot shifting. I'm hard on it down the straight at Snotrocket. But whilst I'm hard on it, this oil temperature has just gone up. It's just shifted up instantly. If we go here, this little spike here, which is 1/10, 1.5, a sixth of a second, has gone from 117 to 124 degrees centigrade. But then, interestingly, as soon as you lift the throttle here, I'll highlight that, the oil temperature drops, by a similar amount instantly. And that's just, it's not realistic. So then looking at all of these spikes, so you can see there's one here, there's one here, there's one here, here, and so on. I started to look at, well, what's common at the start of each of these spikes? What could be causing that? I wanted to see what was common. And if we look here, at where this spike starts, the engine speed is at roughly 5,500 RPM. I thought, right, okay, so maybe it's speed related. So I went to the next one. We look at the start of the spike, and it's roughly at the same speed again. If we go to the next spike and look at the beginning, roughly at 5,500 RPM, and and so on. So looking at the start of each of these, it's roughly 5,500 RPM where this spike happens across the board. 5,500 RPM there. The next one, 5,500 RPM. So I thought, right, well, what's happening at 5,500 RPM that could be causing this? Now, one of the things that this engine has is VTEC. And I will show you in the calibration how this works. So I've got a custom function, which, there we go. At 5,500 RPM, this function effectively turns VTEC on, and it turns it off when it drops below 200 RPM, below that value, so 5,300 RPM, it will then disable it. So that's called hysteresis. I won't go into that now, but that means it doesn't flap on and off too, violently. It's on and off nicely. So that's a custom function. And when I look at the outputs, I can see that output 8 is using that function. So output 8 on the ECU is driving VTEC, and that is switching at 5,500 RPM. So that gives us something to think about here in the data, right? Which is the VTEC switching on affecting this? So we can look at that. We look at that function, general purpose logic 1, overlay that. I'm going to get rid of coolant temperature. We overlay that on the chart over the oil temperature. You can now see these red lines are when VTEC is on. And lo and behold, these unusual peaks seem to map almost exactly to when VTEC is on and off. So this was quite revolutionary. So then this makes me think, well, what is it about VTEC that can be shifting the oil temperature up so quickly? So we know that oil doesn't change temperature that quickly, so it may not be a true reading. So then when you think, well, there's two possible causes, one is mechanical, one is electrical. Whilst, VTEC does affect the flow of oil when the solenoid switches on and off, I can't see why it would change the temperature so significantly, so quickly. So all signs lead to it being an electrical issue, because obviously it's an electrical operated solenoid. And so then we start thinking, right, well, maybe the VTEC is introducing noise when the solenoid switched on. And that's, you have the thing called a ground plane in a car, which is basically 0 volts. Cars run on 12 volts, roughly, but 0 volts, which is ground, earth on a car, because the entire chassis is earth. But you can get slight variations in the ground plane because cars are an inherently electrically noisy place. You've got sparks going, you've got motors going, you've got actuators going. All of that stuff creates noise on the car. Cars are inherently noisy, but there are ways to protect against that. And so looking at this chart, it looks like there's some noise on the oil sensor signal, which is being influenced by the VTEC switching on and off. The way to kind of look into this, the way that I approached it, was the oil temperature sensor is what they call an NTC, negative temperature coefficient sensor. And the way that's wired up is like this. So I won't go into the electrical side of it, but this is basically what's called a potential divider. So you've got 5 volts from the ECU, you've got the ground that I just mentioned, and then this resistor here is called R2. This is the NTC. This is the actual temperature sensor within that unit here. So in there is what they call an NTC. Which is basically a variable resistor that changes resistance with temperature. You don't generally use those on their own into the ECU. You have a second resistor in line, and then the ECU input, the analog input in the ECU for the sensor, it sits in between these two resistors. So one is static and one is variable. which is temperature based, and then you read in the middle. Now this R1, this first resistor, is what's known as a pull-up. And I won't go into too much detail why pull-ups exist, but pretty much every input on an ECU will have some sort of a pull-up. It's either built into the ECU itself or you have it external in the wiring. I thought maybe the pull-up isn't the right setting, and the reason why pull-ups are so important is because different sensors have different operating ranges. Let's just have a quick look and I'll try and explain why that is. So if I go to my analog inputs, I've got oil temperature, and it says here that that's on analog 10. So there's about 23 inputs on this ECU. Oil temperature is on analog 10, and I'm pretty sure analog 10 is using internal pull-ups inside the ECU. So there's a software configurable resistor in the ECU that you can select. If I look here at analog input pull-ups, there we go, analogs 10 and 11, you can set a value. And in this case, you can switch it between 51 kilo ohms, or 51,000 ohms, or roughly 3,000 ohms, 2975. And at the moment, it's set to 2975. Now, for those that follow the channel and this project, I've got a spreadsheet. If you want to go to it, you can go to snot.rocks in a browser, and then there's a link to the spreadsheet. Once we get in there, I've got a tab in here called sensors. These are basically transfer functions or linearization curves that show you what the voltage input is at the ECU for different temperatures or pressures, whatever the type of sensor is. So you end up with a curve like this. And ultimately what you want from a transfer function is the angle of the curve, or the slope should have the most amount of change over the required operating window. So this sensor here, for example, this is the air charge temperature sensor, so the inlet air temperature sensor. Generally, you're going to be operating between 0 degrees and say 50 degrees. So you want the most resolution there, and the most resolution is given by the biggest change in voltage. So you can see this slope here in this area between 0 and 50, the slope is going down the most. At the bottom here, it's pretty flat. At the top, it's flatter. But having that steeper slope around the area that you're really interested in gives you the best resolution when you're monitoring. And what that also does is it gives you noise immunity. So if there's very slight changes in voltage, when you're in this part of the curve, you don't really notice it. What would be interesting before we continue is going back to the data here. If we add a new chart, just to show you what the change in voltage is, right? Because that will help us understand. So I think I said it was analog 10, didn't I? Which is the oil temperature sensor. If I open analog 10 here, you can see this is the raw voltage. So this is not temperature value. This is the raw voltage that the ECU is seeing. So for like here, so this analog read here, this is the value we're reading here now in the logs. It's this voltage between the pull-up resistor and the sensor. And if we go to an area like here where we know there's an issue, what we see, I'll zoom in a bit, you can see down here there's a step. When that switch is here, there's a drop in the voltage, which is correct because the voltage changes, the temperature appears to change. But what we see here, just from the point of that VTEC switching, right? This is 0.04 of a second. It's not even 1/10 of a second. You can see. Let's go just a little bit bigger. Not that quick. A 1/10 of a second, roughly. The voltage has changed from 0.161 volt to 0.187. It's roughly a 0.02 change, 0.026 voltage change. Now, that's not a lot, right? That's a really small amount. However, going back to the transfer function, so this sensor here is the pressure sensor, the combo pressure temperature sensor that I'm running on the engine. Now, as you can see, going back to the principle that I said before, in the area that you care about, temperature-wise, you want the steepest slope. But with oil temperature, you're really interested above 80 degrees. So between 80 and like 140, this is where you're This is the operating range that you're going to be in when you're hard on it on track or on the road. As you can see, this transfer function here, it's almost flat. After like 80 degrees, it really starts to flatten out. And that's not good. That means the voltage change, and here's a chart here, right? So at 100 degrees, the voltage is 0.295, and at 110, it only drops to 0.0232. Now, as you saw on that previous chart here, a 0.026 change in voltage, which is basically the noise that the VTEC is introducing to the electrics of the car, is resulting in a temperature shift here from 117 degrees to 124. So it's a 7-degree shift for a 0.026 change in voltage. So what that means is the resolution at this part of the chart here, the way the sensor's been linearized, is there's pretty much zero noise immunity. Like a 0.02 volt shift is resulting in 7 or 10 degrees change in the perceived temperature rating or output of the sensor. And that's not good, right? So we need to fix that. So this chart here uses the pull-up value. We looked in the ECU here. We could see that we're using a 2975, roughly a 3 kilo ohm pull-up. We've got that configured into this chart. So what happens if we change that pull-up value? Now, I said that it's software switchable in the ECU, so I could go to 51,000, and let's do that and see how that changes the shape of the curve. Right, well, that's not going to help us. That's going to make it worse. So going to 51 kilo ohms, that really flattens out the output of the sensor up here. So you've pretty much got no measuring resolution after about 20 degrees Celsius, so that's not going to work. So we went from 3,000 to 51,000. That's the wrong direction. So if we go down to say 1,000, you can now see the curve has got much more resolution down here, right? It's still not ideal because this bit here, this sensor section of the curve, is where the most resolution is. We don't really care too much about oil temperature, room temperature down here. This is not where oil temperature is important. So we need to go even lower. If I go half that, again go to 5,000, you can now see the shape of the curve is getting much more linear at the upper range, but there still may be a bit more we can go. So if I go to say 150 ohms, ideally what we want is this curve down here to be almost linear. This range here at the top end of the sensor's range, we want to be linear as possible. So let's try 150. Right, look at that. So now we've got the ability to measure from say 100 degrees to 140 degrees over, what is that? That's almost an entire volt, which is a huge shift in resolution than what we had before. Let's just go back to 2975. The rate of change, each of these steps here is 0.2 of a volt. From 100 to 140 was basically 0.2, 0.3 of a volt. Not particularly noise resilient. If we go to 150, we've now got a volt. So, you know, it's 3 times the resolution that we had before, and that would make it much more immune to noise. You know, that 0.02 is not going to make much of a difference to the output. Where we can calculate that. If we, you know, the difference now between 90 and 100, or let's say 100, 110 before, where 0.02 would shift that reading almost 10 degrees, it would now have to be 200-300 millivolts. Massive difference. So I think this is where we kind of get to the root cause of the problem. The data that we're looking at here, the oil temperature data, was obviously wrong. You know, oil doesn't shift like that. Anybody that's an experienced calibration engineer or a log analyzer in a race team or something, or in automotive engine development, would instantly look at that and say, well, that's not right. You know, oil doesn't do that. That's a noisy signal. But going back and tracing it through using the data to basically prove that the data is wrong is a useful tool. So coming into solving this type of problem, you need to you need to have the data, but you also need to have the basic knowledge that allows you to understand if the data is to be trusted or not. And in this case, it's just that basic understanding that fluid temperatures don't change as rapidly as the data is showing. And then having kind of a basic electrical knowledge, which is that could be a noisy signal, and then kind of using the data to prove that. Ultimately, this ended up proving that having the wrong pull-up on the input to the ECU for the oil temperature sensor was not giving us the right resolution where it counted, and was allowing noise on the electrical system to give us false readings. Ultimately, if we take the VTEC off of this chart, if we assume that each of these peaks is wrong, the oil temperature is really following this path here. It's the lower end, it's the low part between each of these peaks is actually the true oil temperature. Now what we could do is strip data from these logs that where VTEC is enabled, just take that out, look at data where VTEC is off, and then look at what that curve looks like, which just for interest I did do separately. If you look at the peaks here, oil temperature is getting up to supposedly 140 degrees, which is too high, really, for the oil I'm running, using it on track. What is much more appeasing is if I look at the temperature after you come off VTEC here, it's 126, which is much more expected on track and in engine use. Key thing is here, key message on the summaries, trust your gut, don't always trust the data, but do use the data to validate your gut feeling, and test every theory. If it doesn't look right, dig into it using a good ECU like the LPC8 from Bowder's Control Systems, what I use. Having the data like this and the ability to do the log analysis easily, you can easily trace back what the root cause is of these issues. Hopefully that wasn't too long. Hopefully it was an interesting way to find out a problem, and I'll catch you on the next one.